Alright, this video is going to be dedicated to good old Unit 7 on exponential functions. In this video, I'm going to go through what exponential functions are, the difference between growth and decay functions. I'll model some problems with growth with accounts that are compounded quarterly, functions that are just increasing or decreasing, so basically using those formulas you see at the top. We're going to talk about how to manipulate exponents. So I'll touch upon this table, but mostly I'm actually going to talk about this table, which, can I move this in this frame? There we go. This table where I talk about the three types of manipulations. So I'll mostly talk about that. Okay. Then with regard to that, I'll look at this example 3 that you see. We're going to do some exponential regression and solving problems. We'll also talk about fractional exponents and solving fractional exponents. And that'll wrap up Unit 7 review. So starting from the top here, exponential functions are any functions of the form y equals a times b to the x, where a and b are real numbers. B is going to be greater than 0. And A is that vertical stretch or shift component, which also correlates to your y-intercept. Granted, there's been no shifting up or down. Okay, so this is actually your initial value. Again, unless there's been shifting up or down. And B is what we call your growth or decay factor. So that's what you're multiplying by each time. So exponential functions are functions that grow through multiplying. Okay, so like 2, 4, 8, 16, those are modeling an exponential function. Alright, so for each of the following, state the transformations on y equals a times b to the x. Okay, so if we look at the first guy, this 3 in front, that would be your initial value, but that's also correlating to a vertical stretch of 3. Okay, and there's been no shifting up or down or anything. The rate of growth or decay is coming from this value right in here. So that's your b value. Now, this b value is equal to 1 plus r. To help us solve for this rate. Okay, so again, b is equal to 1 plus r. So if I were to think about 1/4 in terms of a decimal and subtract 1, I'm getting negative 0.75. So this negative tells me that this function is decaying, and it's decaying by a percent of 75%. Okay, so this is a decay function. Now, I knew that off the bat simply because 1/4 is less than 1, so it's decay. If it was greater than 1, you'd expect a growth. Now, the domain of any exponential function is all reals, and the range is contingent upon the asymptote, which in this case there's been no shifting up or down, so your exponential function, granted it's a decay function, looks something like this if I were to plug it in my calculator. The y-intercept at 3. Okay, it's gonna approach this asymptote at the x-axis, so therefore my range is from 0 to infinity. All right, let's try another one. This guy over here. Let me just move this out of the way. Okay, this example. The 4 in front is a vertical stretch of 4. The negative is a reflection in the x-axis. The 2 is its growth factor, so you're multiplying by 2 for every 1 increase in x. And x minus 1 means you took the function and shifted it right 1. Okay. As far as growth or decay goes, this is definitely going to be growth because this b value is greater than 1. If I do 1 plus r equals 2, r would equal 1. Keep in mind that's a percent, so that means this is growth by 100%. Okay, the domain is still going to be all reals. The asymptote is still going to be from 0 to infinity because there is no shifting up or down. All right, this last example. Okay, let's just mostly talk about the percent of decay in this case and the asymptote. This b value is less than 1, so I know it's going to be decay. If I set 1 plus r equal to 0.4, r would equal negative 0.6. So that means we're decaying by 60%. So that's our rate of decay. This plus 4 means that the function was shifted up 9 units, so that means the asymptote is now at y equals 9. So if I were to sketch a graph of what this looks like roughly, I'd say, all right, here's your x-axis, here's your y, here's your asymptote at y equals 9. I know it's a decay function. There's been no shifting left or right. I'd say it looks something like this. Okay, and you could graph this to confirm it. Domain is still going to be all reals. Your range, though, has changed. You're not going to go lower than the asymptote at 9. So from 9 to infinity is now the range. Oh, I just realized, I think I said that the range here in this example was from 0 to infinity. It's actually the other way around because of this reflection. It would be from negative infinity to 0, but if you graph that, you'd see that. All right, whenever you see a negative exponent, bring it inside. So take a look at this guy. See how it's 4 to the negative 2x? Let me zoom in a second. Okay, if I rewrite this as 4 to the negative 2, leave the x outside, negative exponents create reciprocals. So I can rewrite that as 1 over 4 to the positive square, which is 1 over 16. So something that looked like it was growth is actually not growth, it's decay. Okay, so this is a decay function. So be careful, we can be tricky with these. So look out for those negative exponents. All right, some word problems. This first function is just your straight up increase or decrease. So something's been increasing 25% per year, something like that, or decreasing 25% per year. This next one is compounding, and that's compounding quarterly, monthly, etc. Okay, so compounding over certain intervals of time. And this last one is compounding continuously. It will actually say continuously in the problem. And you'll know to use it that way. So Michelle invests $3,500 into a savings account that compounds quarterly. So again, that's telling me I'm using this middle formula. The interest rate is 2%. How much interest will Michelle make in 5 years? Okay, so plugging in. This is her initial amount, so that's going to be P. Her rate is 2%, but I have to express that as a decimal. N is the number of times it's compounding. So if she's compounding quarterly, that means 4 times per year. So I'm going to divide that by 4. Okay, it's going to balance with 4 at the top. T is the number of time in years, so multiplied by 5. Okay, so in my calculator, so the 20. Okay, and then it says to the nearest cent, which is 2 decimal places. So this 9 will round this up to a 0, which will round this up to a 9. So 3790.90. And there you have it. car is currently worth $9,250. The car has been depreciating, so it's going down, over the last 10 years at a rate of 12% per year. How much did the owner pay when it was first purchased? So it's asking, what's its principal value? What did it originally start at? This is what it's currently at. So this has nothing to do with compounding. It has to do with just a straight up decrease. So here's your formula. I'm going to plug 9250 in for A. I don't know P. The rate was 12% as a decimal. And this was over the last 10 years. Okay, so in my calculator, I'll do 1 minus 0.12. Raise that to the 10th. And this is the number I'm going to divide 9250 by. Okay, so to the nearest cent, 0.53. So 33213. 0.53. I think I copied that right. Yes. Okay, so that's how much he originally bought the car at. Lastly, Nancy invests $300 into a savings account at 1.3%, compounded continuously. So this is your formula. How much will she have the account in a decade? So that's 10 years. So I plug in, she put 300 in at 1.3%, so 0.013 over 10 years. Okay, so here I go. E is second decimal. Oopsies, no, that's I. E is second division raised to the 0.013 times 10. So 341.65. Yep. All right. So mindful manipulations, I'm actually going to switch over to that other sheet I showed you. That's this guy. I had made a table just comparing the different types. The first type is the one where we balance the exponent. So let's say I give you a function that's given in terms of t, where t is years. What this says is you had 100, let's say dollars, and you're growing at 20% per year. And I want to know what this function would look like as a monthly model, meaning I want to know what percent I'm growing at per year, or per month, excuse me. So instead of this being once per year, I want really 12 times per year. So in order to do that, I create this outside exponent to be a 12t. But I can't just make things be 12t because then I'd be changing the function. So I balance it with a 1 over 12 on the inside. Okay? So again, this is 12t because it's 12 times per year, and that's what would create a monthly model. Let's say, for example, I wanted a weekly model. If I wanted a weekly model, I'd create a 52t on the outside and balance it with a 1 over 52 and so forth. If I wanted, I'll go in the other direction, let's say I wanted a decade. That means I would want that outside exponent to be 1 over 10t because that would be once every 10 years. But then I'd have to balance it on the inside by raising it to the 10. Okay, we have a ton of examples about this, so take a look at those, but that's the idea. So you're balancing the exponents. So when you're going from annual to another increment of time, we balance. Okay, and so if you wanted to figure out what percent you're growing by per month in this case, you plug this into your calculator, that's your B value. Okay, so this is telling me I'm growing by about 1.5% per month. Okay. The second two examples are pretty similar. you're starting with an other increment of time, meaning like a weekly, a monthly model. So for example here, if t is years, 52t means 52 times per year. So basically, I just gave you a weekly model as an example. From that, I want an annual model. Now, if t represents years, that means I want a 1t on the outside. Therefore, I must bring in the 52. So I've created a 1t because that means 1 time per year. So you're not balancing here, you're just bringing in the coefficient. This is going to be ridiculously huge. If I actually do 1.20 raised to the 52, okay, and I'll subtract 1 from it because that's what I'm supposed to do. I'm growing by, move that decimal 2 places, yeah, a ridiculous number, which actually makes sense. I mean, this was just a random example I came up with. This says you're growing by 20% per week. So over the course of a year, yeah, you're going to grow a lot over the course of a year. The last example is where t is not in years, it's in months, weeks, etc. So in this example, I said t was months. So technically what this is saying is we're going to grow by 20% once every 4 months, which is aka 3 times per year. So however you want to think about that. So once every 4 months, 3 times per year. Okay. Let's say I know I'm growing by 20% once every 4 months, but what if I wanted to know how much I was growing by per month? Okay, if t is months, I want a 1t, which would be a 1 month, because t means once per month. So again, just like type 2, I bring in the coefficient on the exponent, and then I do 1.20 raised to the 1/4. Okay, so this tells me I'm growing by approximately 4.7% per month, as opposed to 20% per every 4 months. Okay, so this is kind of a crash course in this table, but I would definitely take some time and look at that. So here's an example of a type of problem that you would expect on the regions. Last year, the total revenue for Homestyle, a national restaurant chain, increased by 5.25% over the previous year. If this trend were to continue, which expression could the company's chief official officer use to approximate their monthly percent increase in revenue? And it says let M represent months. Okay, so they gave me information about a yearly increase. They essentially want a monthly increase. So every exponential is of the form a times b to the x. So I'm thinking, all right, they had some initial value, and they were growing by 5.25%, which would be modeled like this, 1 plus that percent, raised to the x. Now in this case, x is years. But it doesn't want years, it wants months. So I'm going to force this outside exponent to be a 12x, because what that means is 12 times per year, which is a month. But I'd have to balance that on the inside with 1/12. Okay, so I'm going to plug this in my calculator and see what I get. Okay, 1.00427 raised to the 12x. Now it said let M represent months, so if I wanted 1 month, that's technically what this is representing, 12 times per year, or 1 month. And that's why answer 3 is your correct answer, because that's your increase per month. Now this looks tempting, but keep in mind that the M/12, if M means months, technically that means once every 12 months. And we know it's not increasing by 0.4% per year. We know it's increasing by this amount per year. So that's why that one's out. All right, regression. You do this in your calculator. Have this be your L1, have this be your L2. Now, if this were in terms of years, like let's say this was 2000, this was 2002, 2004, 2006, 2008, you'd always set that first year to be your 0, and then it was years since the beginning. Okay, so in this case, I kind of saved you a step, but just keep in mind that if I gave you it in terms of a calendar year, change it to 02468. Okay, I'm going to erase that for now to get rid of any confusion. Alright, so we do stat, edit. Gotta clear out some stuff here. Alright, so I got 0, 2, 4, 6, how far did I go? 8. On the other side, I'm entering these in. Okay, good. Now this is going to be exponential, so I'm going to do an exponential regression, also because it told me that. It said find an exponential regression equation. So if I go to stat calc, exponential regression is option 0, I believe. Whoa, where'd it go? No, close that. Sorry about that. There it is. Alright, I have the old software here, so I actually have to manually enter in second L1, comma, second L2, because I'm telling my calculator where the data is. You guys have a prompt screen, which is much nicer. And there you have it. So, anytime you do an exponential regression in your calculator, it's giving you the yearly increase. So what this is saying is you initially have approximately 5.17, according to the best fit model. I know it says 5, but 5.17 is the best fit. And you're growing by about 9.3% per year, according to this. So, it says to round to the nearest hundredth. So 5.17 is your A. And your B is 1.09. Okay, let's just say for fun, if they had in here, write an exponential equation for g of t, because that's technically what they're calling their y's, you would write it like this. This would be g of t, this would be t. Using this equation, predict approximately how many years to the nearest tenth of a year it will take for the tree to reach 15 feet. Now keep in mind, feet is technically a y value. They're saying y equals 15. So you need to plug 15 in for your y's. So we're going to find where this function intersects 15. Alright, so in my calculator, I'm going to graph the function. And I'm also going to graph y equals 15. And I'm going to look at a graph. Now, I'm not going to be able to see a lot of this graph because y equals 15 is obviously much higher. I don't know why my calculator is being so weird right now. Hold on a second. It's weird how sometimes the computer calculator messes up just as much as the in-hand one. Okay, so I need to extend my window. Let's go to like 20. So I need to see where y equals 15 comes in. Okay, so it's happening somewhere over here, which means I need to extend my x's. Go to window, go to x max. I'll do like 20. I'm just guessing. I don't even have the answer key in front of me right now. Alright. Okay, there you have it. So this intersection, so this is the growth of the tree. This is the height of 15. So if I want to find in what year since the beginning it would end up being 15, I have to find that intersection. So we do second trace, option 5 for intersect. This says, am I on the first curve? I am on the first graph, so please hit enter. Am I on the second curve? Yes, you are. And enter again for guess, because there's only one intersection. It's not important to get close to the intersection. So 12.36 is your t. So that means within the 12th year, you're going to eventually hit you hit 15 feet. So predict approximately how many years. Okay, sometimes we'll phrase this as in what calendar year would this happen? Because I'm not loving the way that this is actually phrased right now because I feel like that's kind of ambiguous. Oh wait, never mind. It says to the nearest tenth of a year. Never mind. So 12.4. I was going to say another way that we phrase this is, let's say this started in 2000. I would say, oh, in the year 2012, we would end up hitting 15 feet as a height. So that's just another way to think about it. I didn't read to the nearest tenth of a year. 12.4 would be my answer. All right, last couple things to talk about here. Fractional exponents. If you have a number like x raised to a over b, it's power over root, just like a tree, how the roots are at the bottom. So this would be the b root of x to the a. Okay, and that can be rewritten with the a on the outside as well. Those are the same. Okay, so for example here for a, notice how just the x is being raised to the 1/2. So technically this is the square root of x to the first. Of course, nobody writes it like this. This is mostly how you'll see it. But I was just explaining the power over root idea. In b, the entire product here, 3y, is being raised to the 2/3. So that means we're going to do the third root of 3y being squared. Okay, keep in mind this is the square root, so this would be 5x to the power over root. Make sure you include parentheses though, because it's that whole quantity. Now, had I not included parentheses, technically this is what I would have been saying, which is not what I want, right? So that's why you need parentheses there. Okay, what about negative exponents? Just for practice rewriting, I could make this be positive by flipping it to the bottom of the fraction bar. Then it's power over root. Okay, and then just for sake of rewriting, I mean, we're not going to rationalize here. That's technically what it's equivalent to in its radical form. Okay, and then this last example, I'm going to take the m to the negative 1/2 and move him to the top to make him positive. And then I can rewrite this as the square root of m to the first all over 2. Now when we solve these, I need to isolate the thing that's being raised to the power. So I'll subtract 8, so 33 minus 8 is 25. Divide by 5. Now you're going to undo the 3/4 by raising it to the 4/3. Because 3/4 times 4/3 is 1, so you technically just created an x to the first. Power over root, so this would be the cube root of 5 to the 4th power, whatever that may be. This says round to the nearest hundredth, so you could just plug even this in and get it, but for sake of me in video time, I'm not going to do that. Okay, over here, make sure you isolate. So I divide by 2. This will be 1 over 32. Raise both sides to the negative 2/5. So those would undo each other. Now because I have a negative exponent here, I'm actually going to flip this base and then write it as a positive 2/5. So 3a plus 2 is equal to the 5th root of 32 squared. So 3a plus 2 equals, 5th root of 32 is 2, 2 squared is 4. So a equals 2/3. All right, last example, and then I'm done with this video, is if I'm multiplying these numbers, notice how the bases are not the same. I should try to get the bases to be the same. which actually I probably should do this example first then. All right, I'm going to backtrack for a second. What I'm going to do is rewrite 8 as 2⅓. I'm going to rewrite 1/2 as 2 to the negative 1. Now, in doing so, I get the bases the same, so I can solve the exponent. So 3x squared minus 6x equals negative 1. And you go ahead and solve this like you normally would, okay, and solve for x. Over here, I'm going to get a common base. I'll rewrite 9 as 3 squared. 27 is 3 cubed. 81 is 3 to the 4th. Now when you multiply numbers with the same base, you add the exponents. So this is 2x plus 3x minus 9 equals 4. And I'm getting x equals 13/5. Granted, I didn't make a mistake in my adding anywhere. Okay, and that's it. So I've provided at the end of this a link to the Unit 7 review video, which is a little bit older, so you just need to ignore the first question in that video. But I've tagged it in this so that you guys, if you need more practice with Unit 7, you know where to find it.